Hello, everybody. Are you all able to hear me? I think I've turned my mic on. I want to welcome everybody to this daily chat where I talk to people about mathematics and answer just any questions that you have. I'll be honest, this is pretty informal. This is something where I just am trying to be as friendly and approachable as possible in this difficult time. And consequently, the way we're going to run this is that I will be here. I'll be happy to answer any questions that any of you might have around mathematics. Ideally, this time it's actually around math problems, because I'm going to try to improvise some mini lessons about the questions that you're interested in. Now, I want to emphasize that this particular live stream is intended for the general public. If you are somebody who's like crazy into mathematics, the questions that we discuss on our weekend live stream are maybe a little bit more appropriate in the sense that those are all some pretty challenging questions. On the other hand, we can't only teach math to people who want the most challenging questions. In fact, it's really important to let everyone be able to see that even the normal problems that they're working on might not be that uninteresting, shall we say. There's actually a lot you can do. So what I'm going to do here is I'm actually going to turn on my YouTube right here. And that will let me be able to see the kinds of questions that you're asking. And then I'll just improvise lessons as we go. So let me just log in right here. Actually, you guys joined today for the very, very first live stream, and we were doing quite a bit of setup in the beginning. But we very soon will have this down to a science, where actually every single day of the week we'll have something like this. So here we go. What do we have here? And this is fun because I love to interact with people, so I also get to see what's all here. Oh my goodness. Okay. So it looks like we right away got a bunch of questions. Some of them were specific, some of them were general. I want to say that the goal here is that I want to see if we can focus on questions that might be as useful as possible for the general public. And for the general public, I mean, we're not necessarily going to talk about the Riemann hypothesis. I see some people who are interested in questions in calculus. And some people have some things that are in probability. So I'm going to say, I haven't started discussing a particular question yet, in part because I'm looking for a specific question to jump on, as opposed to, talking about something in general. Maybe we'll have some time to talk about some general things in live streams as well. Okay, so I see something that already came up. So somebody has asked about this summation of 1 over x. So now here's a topic that I can talk about that actually will make sense to a wide range of people, and that's the kind of question that I want to talk about in these live streams. Now, you called it summation of 1 over x. I'm going to write it like this because I think it's something that if I write like this, it's clear to everyone what I mean. 1 plus 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 forever. That's the question. What is this? How can we understand something like this? So if you try to do this by addition, you start with 1 over 1 and you get, 1. And then you add half, you get 1.5. You can add 1/3. What's that? That's like 1.83333. It seems like it's getting bigger. And whenever you look at these summations, the key question is, does this kind of blow up? Does the whole thing equal infinity? And this is a very famous type of function. I see some people are saying it's the zeta function. It is, in fact, the zeta function. For those math enthusiasts out there, there is a function where you look at all of these and you add 1 over powers of things like 1, 2, 3, 4. But I want to keep the focus of this to something that everyone can understand. And I want to talk about why this is infinity. Why this is like as big as you want. There are many ways to do that. One way is using something called integrals, but there's an easier way. Let's do this. If I have 1 over 1 plus 1 over 2 plus 1 over 3, I can say that this is bigger than, so we write this bigger than sign, right? It's bigger than if I left the 1 over 1 as it was. Oh, thanks for helping the focus. Very helpful. 1 over 1 plus, let's keep a 1 over 2. But now for the 1 over 3, I'll say that what's bigger, 1/3 or 1/4? I just replaced the 1/3 by a 1/4, and I left the 1/4 as it was. So far, all I changed was this one. We'll keep adding more stuff, okay? But I went and said the 1/3 is bigger than 1/4. By the way, while I'm doing this, I'm going to tell you a fun math fact, which is maybe both fun and sad at the same time. Don't know if you know about this, but McDonald's has a burger called the Quarter Pounder. And this burger called the Quarter Pounder is called a Quarter Pounder because guess how much beef it has? A quarter of a pound. And there was some time, about maybe 50 years ago, 40 to 50 years ago, that another restaurant called A&W was trying to compete with McDonald's. And they made the third pounder burger. And guess why it was called a third pounder? Because it had a third of a pound of meat inside it. There was only one problem. First of all, they made it cheaper too, but somehow nobody wanted to buy it. And they went to ask, like, why is nobody buying our third pounder? And everyone said, well, it's because, of course, the third pounder is smaller. That's why it's cheaper. Well, fortunately on this live stream, hopefully you know that 1/3 is bigger than 1/4. Okay, so this is okay so far. And now I'm going to do some more changes. Instead of 1/5, I'm going to replace 1/5 with something smaller than 1/5 called 1/8. So I'm writing a red circle because it should be 1/5. I see some people said lol. Yep, that's unfortunately the case, right? So it's like 1/5 is bigger than 1/8. That's okay. 1/6, that's also bigger than 1/8. 1/7 is bigger than 1/8. And 1/8 is, well, exactly 1/8. So I'm writing circles around the numbers for which I took a bigger number and I replaced it with a smaller number. It's going to keep going like this. If I keep going like this, the next line would have plus 1/16, because instead of 1/9, I would write 1/16. Plus, instead of 1/10, 1/16, and so on, a whole bunch of 1/16. Here's a quick question. Does anyone know how many 1/16 I would write? It would go from 1/9, 1/10, all the way to 1/16. How many 1/16 would there be? Somebody's asking why. So first of all, the answer is correct. I saw in the chat, 8 of them. There will be 8 1/16 because I would go from 1/9 to 1/10 to 1/11 to 1/12 to 1/13 to 1/14, 15th, and 16th. That's 8. And you're asking why I'm doing this. You'll see very soon. It's really nice to say that this thing which I don't know, this sum of 1/1 plus 1/2 and so on, it's bigger than this thing over here. Why? Because, look, how many 1/4 do I have? Hey everyone, how many 1/4 are here? There are 2 of them, that's right. And how many 1/8 are here? Does anyone see how many 1/8 I drew? Well, that's just counting. 4, good. So now, what happens if I actually add up those 2 1/4? What is that 1/4 plus 1/4? I'm going to draw a blue rectangle. How much is in this blue rectangle? Yes, I see somebody already has seen what's going to happen. This blue rectangle is a quarter plus a quarter. There's 2 of them. It's 2/4, half. Over here, how many eighths do I have? Oh, I have 4/8. And so if I have 4/8, that's another half. And over here I have 8 1/16. It's another half. In fact, it just keeps going. It's just 1 plus a half, plus a half, plus a half, plus a half, and forever plus a half, plus a half. So the point is, like, I'll have longer and longer groups, but each of the groups is 1/2. I got it kind of duck so you can see it up there. But if you add everything together, the right-hand side is actually infinity. So that's why the summation of 1/x is infinity. This is a nice fact. For those of you who know calculus, I'll say that this is related to something called the integral of 1/x dx, as x, let's say, goes from 1 to infinity. It has some relation to this, and the fact that this integral, if you know calculus, this is equal to the natural log of infinity minus the natural log of 1, which is actually infinity. But I'm not expecting that everyone understands that bit, because this live stream is actually meant for people who are not yet at calculus. Okay, so that finishes this first question and this first mini lesson. We'll kind of go along in this way. I will say I actually just enjoy answering random questions that people have. So I see that somebody here has asked, Are there any techniques to find percentages quickly? Well, I'll give you a few techniques to find percentages quickly. If you see that the denominator you can quickly multiply to make 100, that gives you a way to find percentages quickly. Let me give an example. If somebody ever told me, what percent is 3 over 20 as a percent? Remember, percent means per cent. So per is divided by, and cent is century, 100. So if you see something like this, I see people already see the answer. And since 20 multiplies very nicely to make 100, it's like, oh, just times 5. Great, times 5. And so I do the same, 3 times 5, and I get 15, which is 15%. So this is one of my tips. If you notice that your denominator is easy to make into the 100, just do this kind of multiplication. How about things where the denominator is not easy to make into 100? On that one, what I'll say is then a percent can be made from a decimal. And I'll give one example. The example will be a decimal I enjoy very much. It's called 1 over 7. Now, I cannot easily go and take 1/7 and turn that 7 into 100, because actually, no matter what you multiply 7 by, it still has a factor of 7 inside it. So that hope is gone. Instead, you just take a decimal and you move over the decimal point. Let me show you how. But first, I need to make the decimal. 1 over 7 is actually a really nice fraction. If you divide 1, oh, I need to make sure I have enough space for my head. Let's do it over here. Let's divide by 7. 1 point. You write a bunch of zeros. By the way, the fact that the 7 doesn't divide nicely tells me I'm going to have a whole bunch of zeros. And I guess I go with a 1. Oh, I have to write small now. Sorry, guys. Subtract 3, 30. 7 times 4 is 28. Okay, subtract. No. Did I make a mistake? No, I didn't make a mistake. It's okay. 20. Anyone can help me? 7 times 2 is 14. Subtract 60. How long is this going to take? 7 times 8 is 56. Am I going to run out of space? 40. 7 times 5 is 35. Help. 50. 7 times 7 is 49. And I just ran out of space. But that's okay, because if I subtracted there, 50 minus 49 would be 1. So if I actually subtracted it, I would have at the very bottom here a 1. And then I would have a 1, 0. Actually, that would give me back this. I would be back up here. I would have a 1, 0. And 7 times what is with the 1, 0? Well, 7 times 1. So I claim that if I had the space to continue, let's use a different color. If I had the space to continue, I would have a 1, 0, and I would say 7 times 1 is 7. But I just did that. That's over here. 1, 0 minus 7 is 3. And then I'll get a 3, 0, and I just did that. That was with a 4. Do you see that this is a repeating decimal? The point is I already got something that I saw before. So it would continue. 2, 8, 5, 7, and so on. In fact, we often write this as a repeating decimal where we say 0.142857. We draw that bar on top because that means that you go 142857, 142857 forever. And in this case, if I want to convert this into a percent, how do I think of this as something divided by 100? Well, I could do this. What is it divided by 100? That's what percent means. Percent. I need to put something on top, and the thing I put on top should be exactly 100 times of this, right? Because like somehow I've got a number, and that's equal to 100 times it divided by 100. 100 times it is just 14.2857, 142857, and so on. Okay. Can anyone help me write the top as a repeating decimal if you wanted to? This is kind of funny. It's like a decimal in a fraction. But as long as you understand what you mean in math, this is legit. So 14 well, it's 2857. And if you look at what's going on, I have another 285714. So the repeating segment is actually right here, 285714. So if I write the whole thing down, I get 14285714 repeating. So you could say that this is 14.285714 repeating percent. And I wanted to do this with 1/7 just because of the fact that a lot of times you have to do this 1/7. And after you've seen it enough times, you can actually even recognize it's going to be this 142857, which saves you time. Okay. I did see somebody ask another question. So I've always been watching this chat. So I've seen somebody ask a question, what's the best way to learn geometry with the daily challenge? So thank you for asking. What I didn't mention yet is that indeed all of these free live streams are sponsored by the online math course that I run, where I actually also try to improvise lessons about different topics in math. But those are a bit more systematic, where I've made the concepts in order so you can have a complete course. So if you wanted to learn geometry through the daily challenge, yes, we do have an online course entirely about that. And the way that you would learn it is actually just start from the beginning. And the key idea in that class is that instead of like just going through proofs or just being told some things, I actually took each geometry proof and I turned it into a problem where you calculate something. And while you calculate the something, the steps you do for the calculation are the proof of why that fact is true. I chose to do this not because this is the, well, actually, I should say this. I chose to do this, but I was a bit surprised that it's not so easy to find this elsewhere. But I felt that if the work you do while you're calculating through gives you the proof of the geometry, that's a nice way to be able to learn the geometrical idea. And so what I'll give as a suggestion is whether you use our geometry course or not. If at some point you are learning geometry, I recommend that if you're trying to prove something, the best thing to do is to go and even like put some numbers there and go ask yourself, how would I calculate those angles? And you might discover the proof yourself with some actual angles. So again, what we recommend is if you do want to go through that class, just start from the beginning, go through the end, and there will be all these questions in between that will show you all the proofs, but through calculations instead. Another question. So I see a bunch of, somebody says, hi, Mohan from India. Hi, Mohan, nice to meet you too. I'm looking at all of these things and I'm trying to see what might there be? Oh, I see one. What might there be that might have some relationship to high school math? I did see somebody ask about v minus e plus f equals 2. Let's save that for a later talk. In fact, this is giving me lots of interesting ideas of what we can teach otherwise. I will say the v minus e plus f equals 2, I already have a whole class on that. That's actually in the combinatorics course we have. But let me instead talk about these cube roots of unity, because I'll say this is a pretty surprising fact. Okay? Cube roots of unity. What do I mean? All that person is asking is, what is the cube root of 1? I don't know. What's the cube root of 1? Well, does anyone know what you can multiply by itself and then by itself to get 1? Yes, I saw the answer. It's 1. Okay, we're done. We've answered your question. The cube root of 1 is 1. End of story, right? Well, here's the deal. Let's think of the square roots. Anyone know what the square root of 1 is? What's the square root of 1? 69.420. Not entirely sure that could be the answer, but I see that people say 1. And in fact, if you ever write down the square root sign, that always denotes the positive square root. Whenever anyone writes down that square root sign, it denotes the positive square root. But let me ask a different question then. What numbers square to 1? Aha, now I see some other answers. You could also have minus 1. Also, minus 1 works. Okay, so the cube root of 1, does minus 1 work too? Well, minus 1 doesn't work if you cube minus 1. Over here, if you took minus 1, multiply by minus 1, multiply by minus 1, unfortunately, you get minus 1. So minus 1 doesn't cube to 1. In that case, are we done? Well, if we're looking for answers which are what we call real numbers, meaning like numbers that could be either on a ruler or the negative there, then, that would be all the answers. But it turns out that there are other kinds of numbers. In particular, let's talk a little bit about the square root of -1. What numbers square to -1? Does anyone know? I see some people already said there's some number called I. I works. I is a number that squares to -1. That's actually how we define I. I is something we write down to denote a number. It's called a complex number or an imaginary number, hence the I, that squares to -1. But it turns out that I see somebody has said, learning math with Miguel says, how about -I? Yes, -I also works. -I times -I, that's equal to minus times minus is plus, I times I, let's write it like this, I times I, that's equal to -1. So it looks like I have two solutions. So what number is square to -1? Here the answer to this question is either I or -I. But are there any others? Before we go to the cube root of 1, let's talk a little bit about what else could you find in terms of like the square roots of -1. Could there be any others? And while we're thinking of this, could there be any other numbers that also square to 1? So when I think about this, here's what I would say. It's that in order to square to make a certain number, it means that you actually have to solve a certain equation. X squared equals -1. We're sort of trying to solve this if we're talking about what are the square roots of -1. And if you're trying to solve this, let's start with a simpler problem actually. I'll start with just the 1. Because the question is, how do you know that there aren't any other weird numbers out there, weird numbers involving these i's, that might also square to 1? Here's an easy way to think of it. It's like, how can I solve this equation? Well, we could subtract 1 from both sides. These two are the exact same equation in the sense that I just added or subtracted something from both sides. Whatever x's satisfy the top equation also satisfy the bottom. Whatever x's satisfy the bottom also satisfy the top. But now we're going to do something called factoring. So this x squared minus 1 actually can be factored as x minus 1 times x plus 1. Those are actually the same thing. Watch, I'll just go multiply it. X minus 1 times x plus 1. This equals, you use this method that in America we call FOIL. First, what is it called? First, outer, inner, last, where you look at all the different ways to combine. Like you could put the x and x together and get an x squared. You could put the x and 1 together, or the minus 1 and x together. That's called plus x minus x. And lastly, you can put the minus 1 and plus 1 together to be minus 1. And what this all becomes is it's just x squared minus 1. So good. Oh, I'm a bit of a perfectionist. I don't like how that's yellow. Let's change it to blue as well. Okay? So this x squared minus 1 is exactly this thing here. And so now there's something very important, which is that if I'm looking at an equation where something times something equals 0, here's like, because I'm talking about why all these things are true. Does anyone know the only way to get two numbers multiplied together to make 0? What must be true about at least one of those numbers? I'm looking at the comments to see if anyone can say. Yes, I like it. So Dev Gundala says, use your new method that you just invented. You know, we could. I'm going to jump to cubes. I want to talk about cubes as well. But indeed, somebody says it's exactly if one of them is 0. So basically, let's go back to white. So basically, this thing, that equation, is true exactly when x minus 1 equals 0 or x plus 1 equals 0. And indeed, this is related to this method that I was telling about another way to solve quadratic equations. But what I'm saying is that there's a two-directional arrow here. What that means is that all of the solutions, there are no other solutions. The only solutions are x's for which either this is true or that is true. Nothing else will work. Because you make any other x, and the left-hand side will be not 0 times not 0. Okay, so now I know that there are exactly two solutions. X equals 1 or x equals minus 1. And these are also both directions. It's what we call if and only if. Okay, so now I know that for x squared equals 1, there's exactly two solutions. Actually, I can use the same thing for the x squared equals minus 1. This is a factoring that it's not quite fair to do, but you can do it. I won't draw the arrows this time on the left side, but that equation has the same solutions as this one, right? I just added 1 to both sides. Now can anyone tell me a clever way to factorize this one? I want x with something times x with something, and it should be 0. This time you won't be able to do it with plus 1 and minus 1, but there is something you can write in there that might use an imaginary number. Does anyone see this? I see some people say you can't do it, but you see, you can't do it if you have to use what we call real numbers, but you can do it if I'm allowed to use imaginary numbers. Yes, I can use x minus I times x plus I. It actually works. If I was to multiply that out, just watch. X minus I times x plus I, that equals x squared, and then it's like plus FOIL, right? So the next one is plus ix minus ix, and then minus I times I, which if you simplify is just x squared. The middle terms cancel, which is great, and minus negative 1 I times I, which is x squared plus 1. Bam! So now when I have this, I find out that the solutions are exactly x equals I. Sorry, let me not skip a step. The solutions would be x minus I equals 0, or x plus I equals 0, and this gives you x equals I, or x equals minus I. So that's how I know there's two solutions to this and no more. So now, let's go to the mysterious x cubed. What can we do with this x cubed? I need to know, how can I make x cubed equal to 1? Okay? I want to show you a bunch of ways that you can solve this problem. Yeah, I'll show you a bunch of ways. One of them is easier to understand. One of them is significantly harder to understand. I'll start with the easier to understand, which also is like a really clever trick. Just as before, I need to know how to solve this. Okay, now I want to factor it. But most people don't learn how to factor if I have a cube. You know, normally when we factor things, we factor quadratic equations. But here's something that's useful to know. And in this particular mini lesson, maybe I won't prove it just because we've spent so long on this question already. Ask me the same question like another session, another day, and I'll give you the whole explanation. But if I already know that 1 is a solution, it actually turns out you can always then factor out x minus 1. That's a really cool fact. And we can talk about that in another session, maybe this week or another week. Just ask me this one in particular. But this is a hint that says we should be able to do that. Can anyone help me finish the factoring? Well, if I want to finish the factoring, let's put some things that have to be there. First of all, what should be in the front? The factoring means that I need that this x minus 1 times that thing needs to be x cubed minus 1. So now, that means I need to put something in front so that that times x gives me the x cubed. What times x is x cubed? Oh, I see some people already wrote some stuff down, but we can do it step by step. X squared times x is x cubed. That's very nice. Also, I know something that has to go at the very, very end, the very tip of this. The tip of this will come from like the minus 1 times this thing is the minus 1. Minus 1 times what is minus 1? Minus 1 times 1 is minus 1. So the last thing is plus 1. And in between, I'll have something involving x. I don't know. What should I put in the middle? There's some space here. I have an x squared thing. I'll have to put something here. And I also have a 1. So something here in the middle has an x. Here's a way to think of it. There's going to be something x Let me use another color that's clearly another color, not just something similar to white. That's clearly another color. I left a gap here. I don't know if it's plus, if it's minus, if there's some other number in between. But let's think about what happens when I start to expand these brackets. I will do the x and the x squared, and that gives me the x cubed. Right? That gives me the x cubed. Also, I'm going to do the x times whatever that is. That's going to give me some x squareds. And I'm also going to do this part. This part is going to give me minus x squared. So from the, I don't know what we like to call this color, pink or something? Let's call it pink. From the pink terms, I'm definitely going to get a minus x squared. That's from the minus 1 and the x squared. And I also have some other mysterious thing, some other x squareds. Well, what do I need? I don't want any x squareds. Look at this. I have x cubed minus 1. I want 0 x squareds. How do I get 0 x squareds? By having 1 x squared. I want 1 x squared right here. I'm going to use green. I want that this is one single x squared. So that means that I would want that whatever this x is combining with, when I multiply, I get a positive x squared. Looks like I can do that by putting a plus sign. Does this make sense? I'm just showing how you can reverse engineer this famous factorization. Of course, some people have memorized this, and if you've memorized this, it's very fast. But what I like to show is even if you forgot, you can reverse engineer it. And now I actually want to go through this multiplication just to show how nifty it is. Watch what happens when I multiply x minus 1 times x squared plus x plus 1. I'm going to do that with a grid. I was just in New Zealand, and I found out that the way they multiply is with a grid. So let's try this. X squared plus x plus 1, they draw a grid in New Zealand. And that's multiplied by x and minus 1. And now let's go and fill out the grid. Because in the grid, you got to put like one of each thing together. I see somebody said it's 2:30. Right. Oh, you're talking about when tomorrow's live stream is. Yes. I'm trying different hours through this week just to see what works best for people. So we're doing 2 o'clock until 3 o'clock today, and then we just add another 30 minutes every single day after. Let's multiply. X squared times x cubed. But now I'm going to use colors. X squared times minus 1 is minus x squared, but the x times the other x is plus x squared. I used green just to show that they're the same, just off by a minus sign. Look what else happens. The plus x times the minus 1 is minus x, and the plus 1 times the x is plus x. Oh, look, the blue cancels too. And lastly, I have the minus 1 times the plus 1, which is minus 1. So when you put all of this together, there's all this nice canceling that goes on. These two cancel each other, and these two cancel each other. So I find out that when I multiply together x squared plus x plus 1 times x minus 1, I just get x cubed minus 1. And this is an easy way to see why this is true. Going back here, now we can actually figure out what are the solutions to x cubed equals 1. Watch. On the one hand, if I already have this factorization, I have something times something equals 0. So that means that the solutions are precisely when one of these two is 0, or both. So that means the solutions, all the solutions, are when x minus 1 equals 0, or x squared plus x plus 1 equals 0. Okay, now the x minus 1 equals 0, that's easy. I know what that is. That is x equals 1. How about the other one? Well, for the other one, we just need to know what are the solutions to x squared plus x plus 1 equals 0. So in that case, what are those? What are the solutions to x squared plus x plus 1? Again, because I've gone so long on this question, I'm not going to use the next part to introduce another way to solve quadratic equations. We'll actually jump in and use the quadratic formula, which is totally legitimate to use too. But the solutions to this are x equals, what would you have? Again, you could factor it. You could use that factoring trick, or you could use the quadratic formula of negative b plus or minus the square root of b squared, b is 1, minus 4ac, oh, a and c are both 1, all over 2a. Oh, look at that. So if you do this, then what you get is you get minus 1 plus or minus square root of negative 3 divided by 2. What would that be? Well, that's where you have a complex number. Actually, I saw some people talking in the chat. It's like, yes, we are using complex numbers only because they pop up inside this quadratic formula. But the benefit of this method is I didn't have to tell you about multiplying complex numbers by rotation. I'll say a comment about that after we're done. I just wanted to show you that this method lets even an Algebra 1 student who has learned about the quadratic formula solve x cubed minus 1. Solve x cubed equals 1. Pulling this up, you get negative 1 plus or minus I root 3 over 2. And so those are the solutions. 1 and this mysterious number. And this mysterious number actually works. We won't spend more time on it in today's lesson, but if you multiply this number, like with the plus or with the minus, multiply by itself, get 3 of them together, you actually will get 1. So these are all the solutions. There's no more. It's very satisfying that we have all the solutions. For those of you who know about complex numbers, it turns out that this complex number in particular is beautiful. Let me draw the complex numbers how you usually graph them. So again, my numbers are plus 1 and minus 1 plus root 3 all over 2 and minus 1 minus root 3 over 2. If I want to draw these, what you learn in an Algebra 2 class is that you can actually draw complex numbers by getting some axes, okay? And let me tell you where I would draw plus 1. I would draw plus 1 right here at 1 across, okay? So somehow this x-axis is telling me the not I part. The technical term is it's called the real part. But I think for people who haven't learned this before, this might make more sense. The not I part. There's one not I part. Well, I guess that means the vertical thing is going to be the I part. I part. Okay, so let me try to draw where the other things are. Oh no, I have a typo. Thanks for anyone who caught this. You're confused. You should be confused. There's missing i's here. Okay, these i's are outside the square roots. Now it's better. I hope you're not as confused now. It's just I'm showing you that if I have these numbers, here's how I could try to draw them and look at it. And if I draw this one, minus 1 plus root 3i all over 2, where that would go is that would go to negative half across. Let's use this. Negative half across. And how much up it would go is it would go root 3 over 2 up. What is that? Root 3 is about 1.7. So half of that is about like 0.8 or 0.9. Maybe that's around here. Root 3 over 2. And I would draw this dot here. That dot is negative 1 plus root 3i over 2. So I'm going to say that one is here. And the plus 1 is, all the way over here. And then where might I draw? Where might I draw the other one? This minus 1 minus. Yeah, people are calling these imaginary axes. That's true. And also, yes, when I say root, I mean square roots. Thank you for everyone who's chatting at the same time. But the other one, we would put with a height of minus root 3 over 2, which is around here. And that's around here. Okay? So I have these 3 points. And these 3 points, oops, that's ugly. We have these 3 points, and these 3 points are the cube roots of 1. Who's coughing in the back? Actually, we've got somebody who's helping with the live stream. Unfortunately, as you know, not everybody is well. Fortunately, she does not have the coronavirus, but we are in the middle of a flu season as well. But what we are doing is even when some of us are maybe not as well, we want to make sure everyone can still learn math. The production we're doing today of being able to give you this live stream can only be done by having a team of people to help put all of this together. So thank you for your consideration and concern for that person. So now I want to talk about this particular 3 dots. Do you see anything that looks kind of beautiful geometrically about these 3 dots? It's beautiful. These aren't just like 3 random dots. How are they spaced? What does it look like has just happened? What have I drawn? If I wasn't in an algebra class, and if I was in a geometry class, what would those 3 points be? They're a triangle, that's true, but they're an equilateral triangle. Look at those lengths. In this equilateral triangle, first of all, let's go and check. Is it really equilateral? Equilateral means all the lengths are the same, right? Can anyone tell me how long is this yellow line that goes from plus root 3 over 2 up there down to minus root 3 over 2 here? Does anyone know how long that is? That should be the amount above plus the amount below, which is just square root 3. So this length is square root of 3. Okay, what about the other lengths? How might I try to figure that out? I guess we're going to be reviewing lots of math in this class. This is fun. This is why I like doing improvisational math. How long is that line? To figure out how long that line is, we might have to make a right triangle. I see someone's really excited. Also square root 3. Well, it should be because that's what the answer is going to be, right? But I want to show you how you could figure out that length. No formulas needed. You don't need to memorize any like distance formula between points. I always think of it as the Pythagorean theorem. Because if I just go and look really closely at this slant, can anyone tell me how high that slant is? What's the height? Sorry, let me draw that line again to be more vertical. I drew that slanted line. Let's pretend this is really a straight line. And let's draw another horizontal line across here. Does anyone know how long that green line is over here? Yes, square root 3 over 2. Okay? Yes. Finally, something you know. Okay, thank you for commenting that. What I'm going to do is, as we get more and more people joining these live streams, we might even start to partition off different segments to be talking about different levels of math. It's just because we have just started this live stream, so we're getting like all kinds of questions from all over. I applaud you for sticking through it, even though you saw things that you didn't understand. Actually, when I was young, that's how I got to see what else there would be to learn later in math. But don't you worry, if we can get more people to join this live stream, we'll soon be able to section it off and be like, this part's for Algebra 1, this part is for geometry, and so on. Okay? So that height is root 3 over 2. Let's put a right angle here. How long is the blue part? It's going from, it's at the 1 over here, and it's at the minus 1/2 over there. So how long across is that blue part from here all the way to there? From negative 1/2 to positive 1. 3 over 2, that's right. 1 plus half, 3 over 2. Now, how do I figure out this yellow thing? We could Pythagorean theorem it, right? If you Pythagorean theorem it, let's see, let's call it C. Do I have enough space with my head here? I know what I'll do. I'll draw it over here. Something equals c squared. Pythagorean theorem says a squared plus b squared equals c squared. So I should square the root 3 over 2. That squared plus square the 3 over 2. There are more efficient ways to do this, but I just want to show you how to get through it. What is the root 3 over 2 whole thing squared? I should square the 3, and I'll get, square the root 3, I'll get 3, and it's divided by 4. Root 3 over 2, whole thing squared, is 3/4. And the other one, oh no, I forgot a squared! Thanks to everyone who caught that. Okay, there's a squared missing. That has to plus 9 over 4. That equals c squared. Okay, maybe we have enough space underneath to write down what is 3/4 plus 9/4. It is 12/4. And 12/4 is 3. I see somebody said yay, I agree, yay, we got yay. So it's, c squared is 3, and so the c is the square root of 3. And look, they're all square root of 3. How do I know the other one is also? This is where mathematicians like to say, by symmetry. Symmetry is something that saves you so much time. If you can say, well, you know, the top is up there, the bottom is the same distance down, it's symmetric, so it's also, it's square root of 3, equilateral triangle. And what you'll learn in Algebra 2, when you learn more about complex numbers, is that the cube roots of 1 are these endpoints of the equilateral triangle, where you have 1, because obviously 1 is a cube root of 1, and just draw an equilateral triangle. And if you want to know what the fourth roots of 1 are, what do you think that might be? I won't have time to prove it today, but we can at least talk through it. What are the fourth roots of 1? Should it also be a triangle? Well, maybe. How many roots might there be? The number of square roots was 2. The number of cube roots was 3. How many fourth roots might there be? I guess 10 million. No, 4, right? 4. So if there are 4, let's make a square. And one of the corners of the square is there. So I guess I should try putting the square. Here's 1. I should put the square like this. Here's a square. Okay, square. And this is at -1, this is at +1, and this is at -1. But what do those mean as imaginary numbers? This imaginary number is not imaginary, it's just 1. This imaginary number is not imaginary either, it's just -1. I'll draw circles to show that those are the numbers. What imaginary number does this one mean? Well, remember, one of these axes is the no I part, and one of them is the I part. And so that means that it has no I, that's 0, and it has 1 I. So this is actually I. And this thing over here is -I. Does it really work? Are these the 4th roots of 1? Let's try. What happens if you multiply I times I times I times I? I guess I should first multiply 2 of the i's and get -1, and the other 2 i's and get -1. I just did this and this. And -1 times -1 is +1. It works. And in general, if I want to know the 50th roots of 1, I just have to draw a 50-sided polygon that goes all the way around where one of the corners is on 1. This is stuff that you'll learn in Algebra 2. Okay, we had some fun talking about this particular topic. I will say this is what this kind of live streams will look like. Anyone who watches these live streams is going to end up sort of learning concepts from all over math, where I'm going to try to always explain the concept in as simple language as possible. I appreciate how sometimes people comment in the chat and say, hey, can you maybe say a little bit more? That gives me a cue that maybe the things we're talking about are too hard. I saw some people asking about Euler's identity. Let's save that for another chat where we maybe even specifically restrict to, well, recommend for people who are already in Algebra 2. Euler's identity is directly related to what we've just done here, because this is related to e to the power I times theta. Okay, let's roll to another question. We have about 13 minutes left. Let's see how to put a quadratic function into vertex form. Okay, so this I like because this lets me talk a little bit about something called completing the square. So if I want to put a quadratic into vertex form, so let's give an example here. Quadratic. What's my favorite quadratic? I don't know. Let's make up some quadratic. X. Oh, let's put something in front of the x too, like a 2. Why not? 2x squared. What else can I put here? Let's put like minus, I don't know, 6x plus, let's choose some odd number, like 5. Okay? So this is now a quadratic. But what you're thinking about is you're thinking about graphing this quadratic. That's what you mean by vertex form. Graphing, what that means is that you are going to draw a graph. And what you do is whatever x is, like this is the x-axis, and this is your y, and you're going to say, like, suppose x equals 0, and I put it into here. Oh, you might ask, what is y? Well, a lot of people actually write these as y equals this. I ran out of space on the left. Let's pretend I wrote y equals this all in one line. So if x was 0, does anyone know what y would be? It would be 5. Okay, so if we're going to put 5, I would have to go like 5 up. Let's pretend this is 5. This would be one of the points. When x equals 0, y equals 5. What if x equals something else like 1? What happens if I put 1 in? If I put 1 in, let's just do some scratch work here. If x equals 1, then y equals 2 times 1 squared minus 6 times 1 plus 5. Okay, so this is equal to 2 minus 6 plus 5. This is hard. Oh, it's 1. That's not bad. It's 1. So when we're at 1 over here, y, when x is 1, y is 1. And you kind of like draw all of this together and connect it. So now there's something about how you can connect this. It turns out that if I was graphing a very simple thing, like y equals x squared, then it's nice. Let me just go back to another thing and just draw. What is y equals x squared? Whoops. Oops. Sometimes my pen is a little bit wonky. Let's see. Y equals x squared. This is not bad to graph, because it turns out that when x equals 0, y equals 0. When x equals 1, y equals 1. When x equals minus 1, y equals 1 also. And in general, you end up getting something that looks like a smile. This is called a parabola. Okay? So that's y equals x squared. What this vertex form means is that, by the way, I could draw some other things related to this. I could draw in green y equals 2x squared. And what that would do is when x equals 0, y equals 0. And when x equals 1, y equals 2. When x equals minus 1, y equals 2. And y equals 2x squared would look something like this. In America, many people use a graphing calculator to draw this, and then you'll be able to see the picture. But it will end up looking like that green line. Now, there's something else you could also draw. You could also decide to draw y equals 2x squared plus 1. What would that do? That would actually take your green thing, and it would actually shift it up. So, some people say it isn't fair. Okay, we'll always be trying to find the best way that we can reach as broad of an audience as we can. So I appreciate all of your feedbacks. We're going to try to keep figuring out the best way to do this. But if I have y equals 2x squared plus 1, then let's try plugging things in. When x equals 0, y equals 2 times 0 plus 1, which is 1 now. And when you plug in 1, y equals 2 times 1, which is 2, plus 1 is 3. That's actually up here. Actually, what's going on with this purple or pink curve is the pink curve is not really steeper. It's just that it's the same curve as the green curve, just shifted up by 1. It's like I just took it and I pushed it by 1 up. I just pushed it up by 1. So if I go from green to pink or purple, I just push up by 1. And so when I'm looking at something complicated like this, I wish I could write it as just like, 2x squared plus 5. Unfortunately, though, it isn't, because there's some annoying x term inside. And so what you can do instead with this is you can use the idea that if, for some reason, I could draw the yellow curve, the yellow curve is y equals 2 times x minus 10 squared plus 1. I chose x minus 10 because that's going to give me some space, okay? What would that yellow curve look like? At first, it looks like it would be a mess. Like, do I really want to plug in 0? If I plug in 0 here for x, then I have 2 times negative 10 squared. That's like 200 plus 1 is 201. It's way up there. That's horrible. But I'm going to plug in something else. What happens if I plug in 10? If I plug in x equals 10, that's way over here. But when I plug in x equals 10, I get 10 minus 10. 10 minus 10 is 0. So I actually get 2 times 0 squared plus 1. Look, I would get 2 times 10 minus 10 squared plus 1, which is the same as 2 times 0 squared plus 1. What that means is it's exactly the same height as the purple curve. I want to emphasize I had the purple curve here, and this yellow dot is telling me that at 10, I have exactly the same height. But this is cool because you can actually just shift everything over. For example, if I had 11, if I wanted to know what was at 11, oh, my head's in the way. If I wanted to know what's at 11, I could say 2 times 11 minus 10 squared plus 1. And by the way, that's the same as 2 times 1 squared plus 1. So whatever you want to know for your height of the yellow curve at 11, that's the same as the height of the purple curve at 1. 11 is 1 plus 10. So I'm actually just going to slide the purple curve across. This curve right here, whoa, that looks too steep. Let's do it again. This curve right here, which is the yellow curve, is what you get if you take the purple curve and you slide it over by plus 10. This is what we call the vertex form. The vertex form of a parabola is something times x plus or minus something squared plus or minus something. And finally, let's do the actual problem we had. If I have this, I need to make it look like that. And this is like some algebraic calculation. I would have to take it as, I need 2 times something. So let's take 2 out first. 2 times x squared minus 3x. Okay, I like to do it this way. I'll write plus 5. Okay, the reason I like to do it this way is because the 2 times part is going to affect the x squared, it's going to affect the x, but this extra piece is just going to be whatever is left over. And now I need to make a square. Completing the square is when you do something like this. It's when you say, okay, this is 2 times. It's actually going to be, watch, this will do something interesting. Okay, I'm not done yet. There's going to be more stuff I'm going to write over here. Okay, we're not done yet. But why is that interesting? The reason that's interesting is because if I calculated x minus 3 over 2 times x minus 3 over 2, well then, if I just multiply the x's first, that's x squared. The FOIL thing that we did before would give me x times minus 3 halves, minus 3 halves times x. Put the two together, you get minus 3x. And in fact, after a while, you get used to the pattern that the x thing is double of this 3 halves, which is exactly how I thought to put the minus 3 halves there. And then plus 9 over 4. Okay, so this is completing the square. Now, given that this squared, x minus 3 halves whole thing squared, is this thing over there on the right side, I can't really write plus dot dot dot. I actually have to do this. I have to also subtract 9 over 4, and now plus 5. And the reason this is legitimate is because the thing inside the square brackets, would be this thing over here minus the 9/4, which is the x squared minus 3x. This is called completing the square, and this is actually something that people can do whenever they want to find this vertex form. It's a little bit cumbersome, but it's actually the best way to do it. Let's put everything together. This is 2 times x minus 3 over 2 whole thing squared. When I expand 2 times 9/4 minus 9 over 2 plus 5, we breathe a sigh of relief because we're almost done. This is equal to 2 times x minus 3 over 2 whole thing squared. And what's 5 minus 9 halves? Well, 5 is 10 halves, minus 9 halves is plus 1 half. Wow, that's a beautiful number. I didn't expect this to work out nicely at all. Finally, if I want to know what that really looks like, if I were to graph it here, what that tells me, based on what we had done before, is it's taking a parabola, the y equals x squared, it's going to shift it up by half above the x-axis, and it's going to take the whole thing and shove it over by 3 halves. So in fact, it will probably look something like this. The axis of symmetry is at 3 halves, which is 1.5. It will look like this. And in fact, the picture even looks sort of right. The picture is like above by a half. That's how you do it. So I hope that this thing was somewhat understandable to the people who are asking this question. I think something that I've learned from this live stream so far is that we have a lot of people of different levels. Some people are asking things like Taylor series. Some people ask about Riemann hypothesis. And we have people who are asking about things that are in Algebra 1. My goal is to go and use the time over the next couple of days and possibly even couple of weeks to try to reach out to people all across the United States and the world who may be at home because of the coronavirus or school cancellations. If you liked what you saw, I encourage you to maybe tell more people to join in. As we see the numbers who are watching this rise, we will start thinking about ways to make certain periods of it recommended for people with different experiences. Because I will say I can tell, for people who have already done Algebra 1, what I've just done might have been like, yeah, you already knew that. Although I hope that this way of looking at it might have given you a fresh perspective. At the same time, I know that for some people who are very new to algebra, you might have thought that what I did with these complex numbers was like, what in the world's going on? And that's because some people in this chat have like 2 or 3 years of more experience than you do. I will say, I want to also thank somebody asked the question, AOPS or Daily Challenge. I'm friends with Richard Russick and all the people at AOPS. I'm not here to go and tell them that they're not good. They're also a nice resource too. My recommendation is that for every single person, go and find what works for you. And in the end, what all of us who are doing education are trying to do for you is we're all trying to make choices for you. And my advice is always go and try everything out and decide what works best for you, and that will be the answer for you. I guess that sort of brings this live stream into a close. If you liked what you saw, I hope that we'll maybe see you at other times. But I really hope that we can help to make this into a national or international phenomenon. Because to me, the fun part is to come up on the live stream, to not know what kind of random math questions I'm going to be given. And I find it as a fun daily challenge for myself to say, can I cook up a lesson for this topic right now on the spot? And I'll apologize, sometimes my lesson will not be as good as one that had been prepared long in advance. But I hope that by doing this, I'm showing you how if you just learn to think about math and all the concepts together, you might be able to do all of math. It actually just all fits together. It's not based on memorizing anything. It's just based on thinking. And with that, I'll say, I'll see you all next time. See you.